We have to eventually, what we've been doing was math, yes, but it didn't look very mathy. So I guess we should do some more mathy things. Mathy math, yes. Now, of course, still appropriate for our level, and for our level, aiming at elementary education, we need to get some basic knowledge of how numbers work, not in terms of arithmetic, but in terms of their structure, so to speak. And eventually that structure will become clear as we go. The first topic is that of divisibility. Now, it's not a brand new topic. We just want to highlight a few things. First, by example, stick with this numbering, 9.1. If I take the number 15, I can break it up into smaller numbers. I can use a specific other smaller number, like a 5, and say, well, how many 5s can fit into 15? 3 5s. So I can get 15 by taking 3 5s. I can use another number like 2 and say, how many 2s can go into 15? 7 2s. And then I'm going to have a little bit left over. So in some cases, depending on my big number and depending on the little number I'm trying to fit in, sometimes something's going to get left over, and sometimes there's nothing left over. In the case where so this guy we're going to call the remainder. I think everyone knows that. Remainder. So this is our number of choice here. We'll call that the divisor. We'll call this sort of like an answer when I'm trying to fit the divisor into the number. How many times does that happen? We'll call that the quotient. For some reason, I don't really have a name for that first number. It's just the big number. These are more important names. You can make up a name, but it doesn't really have a name. So, in some cases, the remainder is 0, and in some cases, the remainder is 1. But before we worry about classifying those different ones, let's just find some quotients and remainders. In exercise, I guess it is 9.2. I want to make sure my numbering is correct. So, why is this not? There we go. 9.2? Yeah. So we're taking, I'm going to take this with me because terrible memory. In A, 7925, and we're trying to find the quotient using 7 and how much is left over. Now, yes, you can use a calculator. No, I don't want to. Because of the lower grades, there are no calculators allowed. When did they introduce calculators? Yes, it happens earlier, unfortunately, as the years go, earlier and earlier. Before you know, kindergartens will have calculaters. Terrible thought. What grades do they introduce calculators, or they allow calculators for general use? Not that early. Shouldn't be.
Usually middle school.
Middle school. Yeah, that sounds all right. When the numbers get bigger. And those numbers, like 7, is not big. So if I don't have a basic skill, I have to run to my calculator for even basic things, then I'm not leading by example very well. So how do I find those numbers without a calculator? What is the word? Well, 2 words. Long division. Sadly, long division has an unfortunate name. Because long is in the name, so that just starts you off on the wrong foot. And it's not really long. It's so systematic, it's not long at all. How does that work? Now we've sort of left out division in our previous topics we only did the arithmetic in the different number systems because we're going to do division here just a little bit. So in the end everything is covered. 7 goes into the first digit one time. Then 1 times 7 is 7. I might not have enough space. Oh well. So yes, we only write the 7, but it's really 7,000. You can choose to write that down. I would in the beginning. I'm taking that away. So that you're reminded, especially teaching, you're reminding the student that yes, you're working in the thousands. There are zeros. Maybe we're lazy, but the zeros always also help me to line things up very well. So now I'm subtracting that. If by the method, I'll have no thousands left. 925. Now 7 goes into 9, which is really 900. Once, 1 times 7, which is really 100 times 7, is 700. Take that away, I have 2, I'm running out of space. That's okay. Now I can't fit 7 into this guy anymore, but I can look at the 22 there, which isn't really 22. It's just a convenient way of looking at it. 7 goes into 22 3 times. 3 times 7 is 21. I'm going to squeeze this in here, which is really 210. Take that away, I have 15 left. I think I'm going to make it. 7 goes into 15 twice. 2 times 7 is 14. I have 1 left, and that'll be my remainder. And we usually write it like that. How does that tell me how to break up my original number using 7? It means 7 can fit into this 1,132 times with 1 left over. We have to be competent in, well, more than competent in long division. Though, yes, we actually do it to find stuff. We can use a calculator, but we can't teach a calculator from the start. Only once you've mastered that can you make it more convenient. You can always check your answer in the calculator if you want to be sure. B. 3781. So I'm just going to start 3781 divided by the 4. 4. We'll get to 10. All right. 4 goes into 3. No, wait, that's 4 goes into 37. How many times? Now, you of course practiced your arithmetic, play some raindrops. These things should be really easy. No? 9. 9 times 4 is 36. I like the zeros. Don't want to be too lazy. Take that away and I have a 181. The subtraction is also pretty easy. 4 now goes into 18. 4 times 4 is 16. Take that away. I have 21 left. 4 goes into 21. 5 times 4 is 20. And again I have a 1 left. So I'll write it over here. 3781 can be broken up using a 4 as 945 times 4 plus 1 left over. Six, 4, 1, 5. Divided by 6. Yes, it's easy. We don't do it all the time, so it's worth just sort of refreshing that. Take 30 seconds. to see if you can do it. I could ask it in the quiz by saying use long division, then you don't really have a choice. So we've all done it. We just want to make sure we remember it correctly. And then we'll do it in a few seconds. It's not the hardest thing. We are getting a little more mathy, but it still doesn't have to be hard. Different aspects of math. Some is just pure logical reasoning. Others with numbers gets a little more messy, I suppose. 6 goes into 6 once. 1 times 6 is 6, but it's really 6,000 because I'm working in the thousands. Then I have 415 left. 6 goes into 4 0 times, and I'm not doing anything. I can bring down the 0, but nothing happens. Then I can look at 41. 6 goes into 41. 6 times 6 is 36, which is really 360 because I'm in the tens. Take that away, I have 5 and a 5. Then 6 goes into 55. Every time 1's left over, that's just coincidence. It's not always going to be a 1. Let me ask you this. Yes, it always seems to be a remainder of 1. What numbers could there be as a remainder in this last example? If it's not a 1, what else could it have been?
5.
Could be a 5. 4. 3. 2. No 6? No 6, because otherwise I could fit another 6 in. And our number system practice links very well to that. So 6415 is 1069 times 6 plus another 1 remainder. So now in general we want to be able to say things that don't involve specific numbers. We want to make general statements. So in general, we need to use letters to represent the numbers because we don't know what the numbers could be. We can write our big number as n, maybe. Then our divisor, what should we call it? This is consistent with the book here. Maybe I don't want to use an n, I want to use an a. Doesn't matter. Sometimes I use an N, sometimes I use an A. Really doesn't matter. And I want to use a B for my divisor, simply because they're the first in the alphabet. Then the quotient, we'll use a Q, and the remainder, we'll use an R. So again, we have quotient here, divisor, remainder. There is a restriction on the remainder that we now want to express in our mathematical language. When we set it here in English, mathematically we say R has to be greater than or equal to 0, reading it backwards, but it cannot be this value or higher. So it has to be less than B. So a part of this chapter is just reading the mathematical sentences, the mathematical language that is trying to say things that we could say in English, just more symbolic. And in that sense, it has similarities to just being another language. And we have to be able to read that other language. Okay. So here we could say, well, this is Q, this is B in our previous example, and this is R in the order that we wrote them. Now, in our examples, if we go back to the 15 and the 5 and the 2, don't fall asleep yet. So our example 9.1, we had 15 was 3 times 5 with nothing left over. 15 was 7 times 2 with 1 left over. When the remainder is 0, we say 15 is divisible by 5 when the remainder is 0. In the case where the remainder is not 0, anything other than 0, I don't care if it's big or small. In this case, it could have only been 1, but not in general. We say 15 is not divisible by the divisor 2. That is very much an English sentence. Yes, there are numbers in there, but it's still part of our language. English sentence. How do we translate that to a mathematical sentence? We're saying the same thing. Let's say here in English. How do we say it in the mathematical language? We have the big number on the right, the divisor on the left, and then a line. That's not the same length, not the same height, the longer line between them. And that's our divisibility symbol. Our divisibility symbol. And when it's a not, what is the most efficient way to say it's the opposite of this? By putting a little line through it. A diagonal line. And that would mean it's not divisible. Exactly the same thing to different languages. And we have to be able to read both languages. The English one we can already read. It's just the other one. So that will be our divisibility symbol and not divisible symbol. Now we can say this one in many ways in English, though mathematically there's really only one, and it's that one. But in English there are many ways to say things. One is 15 is divisible by 5. Other ways to say it in English. 5, well, let's do it this way first. 15 is a multiple of 5. Let's not do 5, sorry. Or we can say 5 is a factor of 15. My favorite is 5 divides, I'll say in brackets because I think the into needs to be there, though many books don't say the into. 5 divides into 15. I don't like without the into. It doesn't feel right, but it's up to you. Many ways of saying the same thing in English, only one mathematically. I like the last one because it just feels the most natural when I think about a small number fitting into a big number. But there are other words that they make up for no reason other than to keep you busy, confuse you. There's no need. But I guess they have their place. So we have to know all those words when mathematically it's really very simple and efficient. It's a line. That's all there is. Nothing more.
Please remember to click the like button if you enjoyed the video and to subscribe if you want to be notified of more videos. Thank you.